Okay guys, in this video we are going to talk a little bit more about real solutions and the topic of activities, and we'll also discuss at the end the Debye-Hückel theory for electrolyte solutions. So what we're going to do first is establish a reference for the solvent in a real solution. So this is a solution that is not obeying Raoult's law in the sense that you're seeing deviations from Raoult's law, and we'll look at some figures for that in a second. Nevertheless, when you're talking about the solvent in a real solution, we use Raoult's law as a reference point, even though the solvent is not obeying Raoult's law. So what I'm presenting first here is just what we've already learned about for Raoult's law. So if the solvent were obeying Raoult's law, its mole fraction would be related to the vapor pressure of the solvent in the solution divided by the pure solvent's vapor pressure at a given temperature. And then to express the chemical potential of the solvent in solution, we reference that against the pure solvent plus this correction factor involving the vapor pressures. There's really no approximations in here other than the ideal gas approximation for the vapor phase. That's what gives us this term. But there's really nothing is being said about the solvent in this equation. So this is actually a perfectly valid equation for the solvent. When the solvent is obeying Raoult's law, we make this substitution, and now this is the approximation for an ideal solution, where we substitute for the ratio of the vapor pressures, we substitute the mole fraction of that solvent. All right, so this is going to be used as our reference now for a solvent in a real solution. Now, in a real solution, the ratio of these vapor pressures, that is the solvent's vapor pressure in the real solution divided by the pure solvent's vapor pressure, that is not equal to the mole fraction in general. It'll be equal to some other number, which we call the activity. In this definition, activity is unitless. It's a ratio of two pressures. And to make it look like an ideal solution, or to make this result look like the ideal result, what we do is we introduce a little fudge factor here called the activity coefficient, gamma. Okay, so the activity is some number that's not equal to the mole fraction, but we can write it as the mole fraction times this activity coefficient. And then what we can do is we can take this general result at the top, we can substitute in the activity, okay, and that gives us this result here. So this is true in general. And then using this relationship here, which there's nothing wrong with doing this. You can think, I mean, from an empirical perspective, there's nothing wrong with this at all. It's just that you need to measure the activity and the activity coefficient at every different concentration, which is done in many cases, and the results are tabulated. But anyway, you make this substitution in here, and you'll notice that what I've done here is that we've got, when we substitute that in, we can use the rules of natural logarithms to break this product up into a sum of two natural logs. And so now we have these two parts here, and what I'll point out is that this part right here, this looks like the ideal result. And so that's what I mean when I say that we use Raoult's law as a reference for the real solvent. So the chemical potential of the real solvent, we're using Raoult's law here as a reference. This part of the expression right here comes from Raoult's law. And then we have this correction factor for non-ideal behavior involving the activity coefficient. So Raoult's law is used as the reference for the solvent in a real solution. A few comments here about the ideal limit. You'll notice that if the activity coefficient were 1, then the activity would equal the mole fraction, which would be identical to Raoult's law. So we say that the ideal limit occurs when gamma goes to 1 and the activity goes to the mole fraction, and that will generally be true as the mole fraction of the solvent increases to 1. So as you get closer and closer to pure solvent, the solution will behave more and more ideally. And so here in this problem, they're just having you calculate the activity for a set of experimental conditions. So we're looking at a potassium nitrate solution. It's got a concentration of 0.5 moles per liter. Temperature is 100 degrees Celsius. And the vapor pressure of the solution is 99.95 kilopascals. And at this same temperature, the vapor pressure of water, I have a slight error here. It's not 1.01, it's 101 kilopascals. So what I'll write here is that P star for the water, I'll put for W for water, is 101 kilopascals, not 1.01, that's a typo. And for the water in the solution, so this is what the real solution is doing, it's 99.95 kilopascals. To calculate the activity, it's very easy. The activity of the water will be the vapor pressure of the water in solution divided by the vapor pressure of pure water. And so we take that 99.9, we take the 99.95 divided by 101. And that gives us that the activity coefficient, or that the activity is 0.99. So very close to 1 for this particular solution. Let's talk about the solute next. So it doesn't make a whole lot of sense to use Raoult's law as a reference for the solute, because the solute, in fact, does not obey Raoult's law typically. Typically it obeys Henry's law, as we've seen in one of the previous videos. And we'll look at that again in some of the figures that we'll see in a moment or two. So instead we use Henry's law as the reference for the solute in a real solution. And so here is Henry's law. Here what we're seeing is that the mole fraction of the solute, whatever the species B is the vapor pressure of that solute divided by the Henry's law constant for that solute-solvent combination. And so here what we've got, this is perfectly general right here. Again, it's just based upon the ideal gas law for the vapor phase. So this would be the vapor pressure of the solute above the solution. And what we'll do is we'll replace this vapor pressure with Henry's law. So substituting in for PB, we'll have a term involving the Henry's law constant, and then a term that looks like the ideal result, right, where we just got the mole fraction of that solute. And so now taken together, these two terms here, the chemical potential of pure component B plus this factor involving the Henry's law constant and the vapor pressure of pure component B, note that these are constants. You would know these in advance, or you can measure them separately. These two terms here are taken to be the standard state for the solute in the real solution. Okay, so these two terms here are combined into this standard state of the solute. So we say that the chemical potential of the real solute is equal to this standard state chemical potential plus a correction factor involving the mole fraction. Now, in general, the solute does not obey Henry's law. So this would be for what we call the ideal dilute solution, this result here. But in reality, the mole fraction does not equal this ratio. It's going to be equal to something else, which we call the activity of the solute. And then we make this substitution here. And so instead of being able to express this, this result in terms of the mole fraction of the solute, what we need to do is to make the substitution here. So we've got the standard state, or actually a different way of looking at it is that what we're doing is we're replacing the we're replacing the mole fraction with the activity. Okay, that's what we've done here. And then based on this definition for the real solute, we can separate that into this ideal dilute reference plus a correction factor involving the activity coefficient of the solute. So we can say that the chemical potential of the solute is referenced against the ideal dilute limit, which is based upon Henry's law, plus this correction factor. And like before, when the you can see that when the activity coefficient here goes to 1, then the activity of the solute is the mole fraction of the solute, and that's going to return you to the ideal dilute limit behavior. And that's going to be true for the solute as the concentration of the solute gets very, very small. So the more dilute the solution is in the solute, the more and more like Henry's law that solute is going to be. And so that's what we have. So just to recap these two slides, the solvent is referenced against Raoult's law. The solute is referenced against Henry's law in a real solution. And this problem is very much like the one that we just worked, where they want us to calculate, well, it's a little different. They want us to calculate the standard chemical potential of propanone relative to pure propanone in this in the solution of propanone and chloroform. So they give us the equilibrium, or they give us the Henry's law constant for the propanone. And then they give us the vapor pressure of pure propanone. And they want us to calculate the standard chemical potential of propanone relative to the pure propanone. So what they're having us do, they're having us use the equation that I didn't explicitly write the equation on this slide, but this is the equation. So this is the standard. This would be the standard chemical potential of propanone. It's going to be equal to the chemical potential of pure propanone plus this correction factor involving the Henry's law constant and the vapor pressure of pure propanone. So when they say find the standard potential relative to the pure propanone chemical potential, they want you to in fact evaluate this difference So we'll plug in for the gas constant, plug in 298 for the temperature, and then we've got the natural log of these two, the Henry's law constant divided by the vapor pressure of pure propanone. So starting over here, I'll take the ratio, take the natural log, take that times 298 times 8.314, and I'm getting a difference of minus 1,577 be joules per mole. Here in this example, really these are just some of the graphics that I wanted to show you. So what they've got here, we're again looking at this chloroform and propanone solution. They're having us focus on the chloroform in this case. So first they want us to treat the chloroform as if it's a solvent, and then treat it as if it were a solute. And then they give us various information that we need. And so what we have here below are the measured quantities. So someone has prepared mole fraction solutions with these concentrations for chloroform, and then the vapor pressure of chloroform and the vapor pressure of the acetone are measured. So in order to plot, for example, the activities, what you would need to do would be to evaluate the activity of chloroform as the vapor pressure of chloroform divided by the vapor pressure of pure chloroform. So you would make, for example, a third row here, which would be the activity of chloroform, and you would take the observed vapor pressures for chloroform and divide them by this PC star. Okay, and so that would give you a third row, and then you could plot the activity as a function of the mole fraction. You could also calculate then the activity coefficient of chloroform, which is going to be the activity of the chloroform divided by the mole fraction of the chloroform. So you could also plot this quantity here. So you could plot these two quantities. This would be treating chloroform as if it were the solvent, because I'm using the Raoult's law. Here, I'll write it like this. This is the Raoult's law reference. For the Henry's law, what you would do, so this is Raoult's law over here. Henry's law would be taking the activity to be, let's see, just make sure I don't mess it up here. We would use the vapor pressure of chloroform. Instead of dividing by the pure component's vapor pressure, you divide it by the Henry's law constant. So you would then, this would be the activity treating chloroform as the solute. And again, that's equal to gamma C XC. So you could still calculate the activity coefficients, but these two references, the Raoult's law reference or the Henry's law reference, they're going to give you different values for the activities and the activity coefficients, as illustrated here on these two graphs. So on the left-hand side, this is using the Raoult's law reference, where you would be treating the chloroform as the solvent. Over here, this is the Henry's law reference. These are the numbers that you would get. The blue curve is the activity coefficient, and the red curve is the activity. Notice that the activity coefficient goes to 1 for when the solution becomes pure chloroform. Over here, however, the activity coefficient goes to 1 when it's a very dilute solution in chloroform, right? When the mole fraction is close to 0. This is something that we've actually looked at before, but it's worth doing it again. One thing that I'd like you to know about real solutions, I'd like you to know when you're looking at a pressure composition diagram, I'd like you to be able to identify the deviations from Raoult's law. Are they positive deviations or are they negative deviations? And then what does that mean in terms of the intermolecular interactions between the solute and the solvent? So here's an example. So this would be, I'm not sure what solution it is. It's a made-up solution apparently. And so what this figure is doing is it's showing us the vapor pressure of component A divided by the pure vapor pressure of component, or the vapor pressure of pure component A as a function of mole fraction. And so that gives us this Raoult's law curve right here. And now what's plotted, what these other curves are, these are for different solutions that have different degrees of deviation from ideal behavior. Now the textbook is discussing this excess enthalpy associated with the real solution. We can de-emphasize that in your homework. Certainly I'm not going to have any questions about the excess enthalpy model for deviations from ideal behavior. But what I want you to appreciate is the nature of the deviation. That is, whether it's a positive deviation from Raoult's law or a negative deviation from Raoult's law, like this one curve is here, and to know what that means in terms of the interactions between the solute and the solvent. When you're having positive deviations from Raoult's law, it's indicative of the fact that the solute and the solvent, and in particular the solvent, I guess in this case, or maybe the solute, it just depends on which portion of the graph you want to talk about, it is less likely to vaporize than it would be for the, or I should say is more likely to vaporize than it is compared to the ideal solution. Okay, so when you see a positive deviation from Raoult's law, that means that that component has a higher tendency to vaporize compared to the ideal solution. That means that the interactions between the solute and the solvent aren't as strong as they are in the pure solvent and in the pure solute. Okay, so the way that I put it here on this slide is that the interactions between A and B are less favorable compared to the ideal solution, compared to the separated solutions. Conversely, if you have a negative deviation from Raoult's law, and there's just one example given here on this curve, that indicates that there's a lower tendency for that component to vaporize compared to the ideal solution, which means that the interactions between A and B are more favorable. Now, in both cases, the interactions between the solute and the solvent are attractive, otherwise the solution wouldn't form. And so, you know, there are attractive interactions between the solute and the solvent. It's just relative to the pure components is what we're comparing here. And so for the positive deviations, the interactions are less favorable. For the negative deviations from Raoult's law, it indicates that the interactions are more favorable. One more thing that I'll remind you about. So when this solution becomes pure component A, you'll notice that all of the vapor pressure curves converge to the ideal limit. That is, they all converge to Raoult's law. However, for the case where component A is the solute, that is, when there's very little of component A in the solution, what these lines are converging to are Henry's law. And for these different solutions, there's a different Henry's law constant, right? The Henry's law constant is not unique to the component, it's unique to that type of solution. So in order to know the Henry's law constant, you need to know both what the solute is and the solvent is. And for each combination of solute and solvent, there's a different Henry's law constant. And that's what you're seeing here in these curves. The Henry's law constant is different for each of these solutions. So like as XA goes to 0, the curves do get linear. It's just that the slope for each of them is different. Whereas when component A is becoming the solvent, everything converges to Raoult's law, and so they all converge to the same line. Here's an example showing both components. In this case, we've got benzene and cyclohexane, plotted as a function of mole fraction of benzene in the solution. So as you go from pure cyclohexane on this side of the graph to pure benzene on this side of the graph, you see the vapor pressure curve for benzene increases and the vapor pressure curve for cyclohexane decreases. In fact, this value right here, this would be the vapor pressure of pure benzene. This would be the vapor pressure of pure cyclohexane. And then the blue curve here is the total of the two. Literally just taking this curve and adding it to that curve will give you the total vapor pressure. What I'll ask you to think about, the Raoult's law result, the ideal solution result, would draw a straight line from this point to this point. Okay, so it would be below the red curve. Likewise, Raoult's law would give you a line that goes from this point to that point. Okay, so the yellow curve is showing a positive deviation from Raoult's law, as is the total vapor pressure. The total vapor pressure would be a straight line going from this point to that point. And so we're seeing positive deviations here, corresponding to less favorable interactions between the solute and the solvent compared to the pure solute and the pure solvent. So there's a higher tendency for the solution to want to vaporize. Okay, well, in this last part, we're going to talk about electrolyte solutions and the activity of electrolyte solutions. What I wanted to point out is that electrolyte solutions never ever behave ideally. Okay, so there really isn't a very good ideal limit for electrolyte solutions like there is for, say, a solvent, like a nonpolar solvent. And the reason that that's the case is because of the nature of the interactions between ionic solutes and their molecular solvents. So when you dissolve an electrolyte, okay, it's got cations and anions, and so this reaction here denotes the stoichiometry that you have. You'll have a certain number of cations. So this symbol nu plus, this represents the number of cations in the chemical formula for the ionic compound. The nu minus is the number of anions. I suppose you could write a similar equation for a molecular electrolyte as well. There's nothing to prevent you from doing that. I'm just have it in my mind that it's an ionic electrolyte. In any case, the cations have a particular charge, plus charge, and a minus charge on the anions. And due to requirements of charge neutrality, the number of cations and anions formed in the charges must combine together to give you 0. And then we introduce this other symbol here, just nu by itself. That's just the sum of the number of cations and anions added together. So what we've done previously, where we've discussed the Henry's law reference for the chemical potential of the solute in a real solution, perfectly valid thing to do. Okay, so this is still true. We worked with this previously. This is still true for the electrolytes. Nothing wrong with it. Conceptually, we could imagine breaking the chemical potential of the solute down into different parts. For example, we could break it down as a part involving the cations and a part involving the anions, and then we just need to multiply by the number of cations and anions we have in order to get the chemical potential of the solute. One of the difficulties in working with this approach is that ions always come paired together. That is, you always have a cation paired with an anion, and so you can't exactly measure the chemical potential of a cation independently of the chemical potential of the anion. Okay, so what do? Well, we kind of average things together using what are called mean ionic activities and mean ionic activity coefficients. So here we're saying that the activity of the solute is this A plus minus. That's called the mean ionic activity. So that's one symbol, A plus minus. That's one thing. Raised to the nu power, where nu, again, from this previous slide, is the sum of the number of cations and anions in the chemical formula. So we can further expand that in terms of a concentration unit. So we're going to be using molality here in these formulas. So this is the mean ionic molality, B plus minus. That's one symbol raised to the nu power. And then this is called the mean ionic activity coefficient raised to the nu power. And so these things have further definitions. Okay, now these aren't very practically useful, but they're useful conceptually. The mean ionic activity coefficient, or the mean ionic activity raised to the nu power, is defined as A plus to the nu plus, A minus to the nu minus. Now again, you don't measure these things independently of one another. You can't measure A plus independently of A minus. That doesn't work. You can, however, measure the mean ionic activity. But we need these definitions in order for everything to be consistent. Here at the bottom, we're just saying that the cation concentration, the cation molality, is just the molality of the electrolyte times the number of cations in the electrolytes chemical formula. So nothing fancy there with these equations at the bottom. As I was saying, you can measure the mean ionic activity, and you can also derive a formula for calculating the mean ionic activity if you follow this Debye-Hückel theory. Now, I'm not going to go too much into the details of that. I wanted to just say a few words about the main concepts that are at work in this Debye-Hückel theory, and I'll show you the result. But the derivation is a little involved, and so I've decided to skip it. Okay, so first off, the Debye-Hückel theory only works in the dilute limit. Okay, so you have a very dilute solution for your electrolyte solution. Henry's law is not going to cut it. We need to go a little bit further. What is the basis of the Debye-Hückel theory? Well, first, it involves long-range electrostatic interactions between the ions. Okay? And that's why ionic solutions, or electrolyte solutions, are never ideal. And that's just because the Coulomb interactions between ions is just radically different than the interactions between the ions and water, which are ion dipole interactions. They're very different. Those are very different than the interactions between the solvent particles. And so you're just never going to be in a situation where the solution is behaving ideally. So that's the source of non-ideal behavior, is these electrostatic interactions. However, electrostatic interactions are actually somewhat nice because they can be modeled rather easily. Contrast that with things like hydrogen bonding or London dispersion interactions and even dipole-dipole interactions, which are not so easy to model. The electrostatic interactions are, relatively speaking, well behaved. And since they're the most important feature, that means you can get quite a little bit of headway made using simple models, and that's what the Debye-Hückel theory does. The main idea is the existence of what's called an ionic atmosphere, wherein in solution, each ion is surrounded by a set of counter ions that more or less moves around with that ion. Now, here's a diagram illustrating it. So let's suppose that we've got a cation here, or maybe it's an anion, it doesn't really matter. Surrounding that ion in solution are going to be counter ions of opposite charge. And what these ions do is they lower the chemical potential of that ion. And vice versa. The red ions are going to be surrounded by the blue ions, presuming that those are opposite charges. Okay, so that's the main principle used in the Debye-Hückel theory, the existence of this ionic atmosphere. And then from there, and I'm skipping all the details, you can derive an equation for calculating the mean ionic activity coefficient. So we have the logarithm base 10 of the mean ionic activity coefficient is minus a constant, which for aqueous solutions at 25 degrees Celsius takes on this value. The constant would be different for different temperatures, times the absolute value of the charge of the cation times the charge of the anion. I have a little typo here. This should not be an I. This should be a negative sign. So this should say Z plus times Z minus. And then that is multiplied by something called the ionic strength to the 1/2 power, so the square root of the ionic strength. And so that's another thing that the Debye-Hückel theory introduces, a quantity called the ionic strength, which really is kind of like, it's like the average concentration of charge. So you've got both cations and anions present. The ionic strength represents the concentration of average charge magnitude, so to speak. Here's how you calculate it. You take 1/2 times the sum over every ion. So if you've got different cations and anions present in here, this index I is the index for whatever ions you have. You take the charge of that ion squared, and you multiply it by the molality of that ion. So this should be B subscript I divided by the standard molality, which is just 1 molal. So B naught is equal to 1 molal. Just to correct the formula, just so that I have the correct formula on here, this would be I equals 1/2 sum I Zi squared Bi divided by B0, like that. So you can, if you know what compound you have, and you know the concentration, you can calculate the ionic strength, and then you can use that to predict what would be the mean ionic activity coefficient for that. There are extensions of the Debye-Hückel law that include additional corrections. Okay, you just wind up with more parameters in that equation. So here's another version of the Debye-Hückel law that's called the extension. I believe it's called the Davies extension or something like that. So here in this problem, what we're being asked to do is to calculate the mean ionic activity coefficient. So using this expression here, minus, in order to calculate that, we need to evaluate the ionic strength of a potassium chloride solution. So let's calculate that. So it's going to be 1/2. The cation is +1 charge, so +1 squared times the molality, which is going to be 5, I'll just write it molar, divided by the standard 1 molar, so that's the B0, plus we'll have the -1 squared, and it's going to be the same thing, 5 molal divided by 1 molal. So what is that going to give us? 10 divided by 2, so that's going to give us 5, ionic strength of 5. Then we will take the anti-logarithm, so this will be 10 to the power of minus, and then I've forgotten the value of A, 0.0509. Then we've got the 2 charges here, so it's going to be the absolute value of +1 times -1, so that doesn't do anything. And then we'll take the ionic strength to the 1/2 power. And all of that is to the anti-logarithm. So square root of 5 times 0.0509. Make sure you include the minus sign. And then we'll take the anti-logarithm. And I'm getting 0.769. So that is the Debye-Hückel result for the mean ionic activity coefficient of a potassium chloride solution. Is it any good? So this figure illustrates the circles here are the real values for the logarithm of the mean ionic activity coefficient for a bunch of different solutions, plotted as a function of the ionic strength of that solution to the square root. Okay, so according to the Debye-Hückel theory, if you plot this as a function of the ionic strength to the square root, it would be a linear graph, and this would be the slope, right? So those are the dashed lines for these different types of electrolytes. And what you see when the solution is very dilute, you see that the Debye-Hückel theory works pretty well for all of the solutions. It correctly gives the slope in the dilute limit. But then as you go to more and more concentrated solutions, you start to see more and more significant deviations from the Debye-Hückel limiting law. In fact, that's why it's called a limiting law, is because it's valid in the limit of low concentration. Here is a graph showing you the Debye-Hückel law, the dashed line, compared to the extended law, the Davies equation. This is for something like sodium chloride, a 1,1 electrolyte. And you can see that the Davies equation does better at higher concentrations. However, the caption is quick to point out, as you go to even higher concentrations, you're going to find that the Davies equation breaks down as well. And again, that's just due to the nature of the electrostatic interactions involving ions. They're just very strong, and so you get significant deviations from ideal behavior, which are difficult to model. Okay, with that, I'm going to go ahead and stop this video, and we'll pick up with the next focus on chemical equilibrium in the next one.